In this lecture, we're going to cover electric potential, which is a voltage. Our study of electricity began with Coulomb's law, which calculated the electric force between two charges, capital Q and lowercase q, or Q1 and Q2. By assuming that Q was a small positive charge and dividing F by Q, the electric field E, due to the charge Q, was defined. So the electric field is equal to the force per unit charge, which is K capital Q over R squared. The same process will be used to define the electric potential, or the voltage, from the electric potential energy, where V is a property of the space surrounding the charge Q. So the potential energy, remember from the last lecture, was KQ, capital Q, lowercase q over R. If we take the energy per unit charge, that gives us the voltage or the potential. So the potential is defined as KQ over R, where capital Q is the charge that we're looking at that produces that potential. Just a reminder, the units for voltage or potential is volts. What we've done here is remove the system that was required to define electric potential energy. Remember, we needed two objects, or a field and an object, in order to have energy. Voltage is a property of the space surrounding a single or multiple charges, or a continuous charge distribution, like a plate of charge or a line charge. So here the voltage is defined as the potential energy divided by Q, or KQ over R. It tells us how much potential energy is in each charge, and if the charges are moving, how much work per charge they can do on another system. Voltage is the electric potential energy per charge, which is expressed in terms of joules and coulombs. The units of a volt are joules per coulomb. To make this more understandable, a volt is visualized as a battery adding 1 joule of energy to every coulomb of charge that goes through the battery. What is the electric potential, or the voltage, 5 meters away from a charge of 6.23 times 10 to the minus 6 coulombs? Go ahead and pause the video now and see if you can solve this problem. Okay, so let's take a look at your answer. If you use the equation for voltage, it's KQ over R. Substituting in our numbers, you should have ended up with a voltage of 1.12 times 10 to the 4 volts. If you didn't get that answer, please go ahead and check and make sure that you have your parentheses nested together correctly, or that you're using the EE button on your calculator. What is the electric potential, or the voltage, 7.50 meters away from a charge of negative 3.32 times 10 to the minus 6 coulombs? Pause the video now and see if you can answer this one. Okay, so the voltage is KQ over R. Substituting in our numbers, you should have ended up with a voltage of negative 3.98 times 10 to the 3 volts. So let's talk about electric potential, or voltage. Despite the different size of these two batteries, they both have the same voltage. It's 1.5 volts. That means that every electron that leaves each battery has the same potential, which is the same ability to do work. To get the total potential for multiple charges, you must first find the potential due to each charge. Then you can add these potentials together. Since potential is a scalar, there's no direction involved, but there is a positive or negative sign associated with each potential. So for example, if there are 3 charges, the total potential is V1 plus V2 plus V3, which is the total voltage. The total voltage, again, is the sum of all of the individual voltages. So here's another example. Compute the electric potential of 3 charges at the origin in the following configuration. Go ahead and see if you can solve this one now. Okay, so if you're not done, go ahead and make sure you pause the video. Let's go ahead and take a look at the answer. Okay, so let's go through this solution. V1 is equal to KQ1 over R1. Substituting in our numbers, we end up with 5.63 volts. R2 is equal to KQ2 over R2, which ends up giving us 13.5 volts. V3 is KQ3 over R3, which ends up giving us negative 13.5 volts. When we add all three voltages together, we end up with 5.63 volts. Okay, two positive charges of magnitude plus Q are placed at the corners A and B of an equilateral triangle with side R. Calculate the net potential at point C. So there you go. Okay, so pause the video now and see if you can solve this problem. Okay, so let's take a look at the solution. First, we solve for, I'm going to move this down so we can see it better. Okay, there we go. Okay, so we have the answer. V1 is KQ1 over R1. V2 is KQ2 over R2. Since Q are the same for both charges, and the distance between point C and A and C and B are the same, we end up having the same exact value. So we can multiply this by 2, and we get 2KQ over R, and that's our net potential. Okay, four charges of equal magnitude are arranged in the corners of a square. Calculate the net electric potential at the center of the square due to all charges. So here you go. Go ahead and pause the video and see if you can solve this one. Okay, so here's what you should have gotten. And I'm going to move it down a little bit so we can see the answer. Okay, so solving for V1, V2, V3, and V3, notice that they're all the same exact equation, KQ over R. R is going to be the square root of 2S over 2. Notice that in the diagram, this is S here and here. We want this distance here. If you take the diagonal of this, it's going to be the square root of S squared plus S squared, which is the square root of 2S squared. Taking the square root of that, you end up with the square root of 2 times S. You want to cut that in half because you only want to go halfway. And so that ends up giving us the square root of 2S over 2. So that's where R comes from. Adding these all together, we end up with 4 times the square root of 2 KQ over S. Okay, another helpful equation can be found from V equals U over Q, or potential energy divided by charge. By realizing that work done on a positive charge by an external force, which is a force that is external to the force generated by the electric field, will increase the potential energy of the charge, so that work is equal to QV. Note that the work done on a negative charge will be negative. The sign of the charge does count in this case. How much work must be done by an external force to bring a 1.0 times 10 to the minus 6 Coulomb charge from infinity to the origin of the following configuration? They give you the charge for Q1, Q2, and Q3, and the location of Q1, Q2, and Q3. Go ahead and pause the video and see if you can answer this problem. Okay, so let's see if you have the correct answer. The electric potential of this configuration was found to be 5.63 volts. Positive work must be done to move a positive charge toward an area of positive electric potential. Work is equal to QV. The potential, again, we found by multiplying KQ over R for each one, and then substituting in the charge that we're bringing in, which is a 1 times 10 to the minus 6 Coulomb charge. It ends up giving us 5.63 times 10 to the minus 6 joules. If you're unsure where the 5.63 volts came from, please check the previous examples and where we saw for the total electric potential of the configurations. Three charges of equal magnitude but different signs are placed in three corners of a square. In which of the two arrangements more work is required to move a positive charge, test charge Q, from infinity to the empty corner of the square? First, make a prediction and discuss with your classmates. Well, actually, you're going to just make a prediction and write down your answer. Second, calculate the work done on moving the charge for each arrangement with the given numerical values. So we're going to have capital Q is 9 times 10 to the negative 9 coulombs. Lowercase q is 1 times 10 to the minus 12 coulombs, and S is 1 meter. So we have arrangement 1 and we have arrangement 2. And so what are you trying to find? You're going to find out which of the two more work is required to move a positive test charge from infinity to that empty corner. So which one will have more work? Okay, pause the video now and see if you can answer the question. Okay, so let's see if you have the correct answer. I'm going to have to move it down. Your prediction has to be based on comparing the net electric potential at the empty corner to each arrangement, in each of those arrangements. So in order to calculate work, you need to find the net electric potential and multiply it by the test charge. So here, the sum of V1 is equal to KQ over S plus KQ over S minus KQ over the square root of 2S. That gives me 162 volts minus 57.3 volts, which is 104.7 volts. The work done is Q times that potential, and that gives us 1.04 times 10 to the minus 10 joules. In the second configuration, we have KQ over S minus KQ over S plus KQ over the square root of 2S. And that gives us 57.3 volts. The work done to move the charge from infinity to the corner of the square is then going to be the charge Q, which is 1 times 10 to the minus 12 coulombs, times that potential, which is 57.3 volts. That gives us 0.57 times 10 to the minus 10 joules. So in the first configuration, it takes more work than it does to move that to move the charge into that corner than it does the second configuration. Okay, electric potential or voltage. Consider two parallel plates that are oppositely charged, as shown in the diagram. This will generate a uniform electric field, pointing from top to bottom. This was described in the previous lecture notes on potential and electric fields. A positive charge placed within the field will move from top to bottom. In this case, the work done by the electric field is positive. The field is in the same direction as the charge's motion. The electric energy or potential energy of the system will decrease. This is directly analogous to the movement of a mass within a gravitational field. If there is no other force present, then the charge will accelerate to the bottom by Newton's second law. So we have an external force going up, we have the electric force going down. But if we want the charge to move, if we want it to move to at a constant velocity, we have to add that external force. Because right now, according to the picture, we only have the force due to the electric field. That external force has to be equal in magnitude but oppositely directed to the electric field force. This external force has to point upward. Since the charge is still moving down but not accelerating, the work done by the external force is negative. Okay, so here's our two forces. They're equal in magnitude but oppositely directed. But remember, the charge is still moving at a constant velocity. The work done by the external force is negative. The work done by the electric field is positive because it's moving in the same direction as that force. The net force, and hence the net work, is zero. The potential of energy of the system decreases. Okay, so think about this for a minute. The net force is 0. If the net force is 0, then the work, which is F dot D, must also be 0. The work done by the external force, though, is not 0, and the work done by the electric field is not 0. This means that the work done by the external force must be the same magnitude as the work done by the electric field, but in the opposite direction. Meaning the displacement and the forces must be opposing one another. Now consider the case where we have a positive charge at the bottom and we want to move it to the top. In order to move the charge to the top, an external force must act in the up direction to oppose the electric field force, which is directed downward. In this case, the work done by the electric field is negative. The field is opposite the direction of the charge's motion. The potential energy of the system will increase. Again, this is directly analogous to the movement of a mass within a gravitational field. Now, for those of you that don't understand what this means, if I lift something upward, I'm applying a force upward in the same direction that I'm moving the object. That is giving it gravitational potential energy because it's getting higher and higher. If I were to lower the object, then it's losing gravitational potential energy. If the charge moves with a constant velocity, then the external force is equal to the electric field force, since the charge is moving up but not accelerating. That means the work done by the external force is positive. The work done by the external force is positive to move it upward. The work done by the electric field is negative because the force is going down but the direction of motion is up. The net force, and hence the net work, must be 0. The potential energy of the system will increase because you're moving that charge upward against the electric field, force, the Coulomb force. Okay, so go ahead and let's read through this and pause the video in order to answer the question. A positive charge is placed between two oppositely charged plates as shown below. There it is. Which way will the charge move? What will happen to the electric potential of the charge/plate system? I want you to go ahead and pause the video and write out your answer now. Okay, so let's check and see if you understand what's going down. What's going on, sorry. It is going down and it is decreasing, okay, because it's moving in the same direction as the field. A positive charge is placed between two oppositely charged plates. If the charge moves with a constant velocity, meaning no acceleration, as shown below, what is the sign of the work done by the electric field? Force. What is the sign of the work done by the external force? What is the total work done by the two forces? Go ahead and pause the video now and answer these questions. Okay, so let's see if you have the answers. The work done by the external force is going to be negative. The work done by the electric field is going to be positive, and the total work done by both forces is going to be 0. Okay, similar logic works for a negative charge in the same electric field, but the directions of the electric field force and the external forces are going to be reversed, which will change their signs, and the potential energy is summarized, will be on the next slide. So here, if we have a negative charge, it's going to be attracted to the positive plate, and that means that that's your electric field force going up. That means the electric force would have to be directed down, okay? And vice versa, if you're pushing a negative charge down or wanting it to go down, you have to apply an external force down because the electric field force is going up. Okay, the work done by the external force is negative. Work done by the electric field is positive. The net work and the net force are going to be 0. The potential energy in this case will decrease. In the other example, work done by the external force is positive. Work done by the electric field force is negative. The net force, and hence the net work, is still 0. In this case, though, the potential energy of the system increases. A negative charge is placed between two oppositely charged plates, as shown below. Here you see it. Which way will the charge move? What will happen to the potential energy of the charge/plate system? Go ahead and pause the video now and write down your answer. Okay, the charge will move up towards the positive plate because opposite charges attract. That means that the potential energy of the system will decrease. A negative charge is placed between two oppositely charged plates and due to an external force moves down with a constant velocity as shown in the diagram. Okay. What sign is the work done by the external force? What sign is the work done by the electric field? What happens to the potential energy of the charge plate system? Go ahead and pause the video and write your answers down. Okay, so let's go ahead and look and see what is the sign of the work done by the external force. The external force work is going to be positive. The work done by the electric field will be negative, and that will increase your potential energy of the system. If you don't understand these, please review the previous slides where we go over the difference between positive and negative charges in an external field. Like electric potential energy, voltage is not a vector, so multiple voltages can be added directly without taking into consideration, well, we do have to take into consideration the fact that they may be positive or negative. Like gravitational potential energy, voltage is not an absolute value. It is compared to a reference level. So remember, you can have negative potential energy. It's just below your reference point. So by assuming a reference level where the potential is 0, as we do when the distance from the charge generating the voltage is infinity, is allowable to assign a value, a specific value to V in calculations. In the next slide, we will continue the gravitational analogy to help understand this concept. Okay, so we're going to compare this to topography. Each line represents the same height value as you learned in earth science. The area between the lines represents the change between the lines. A big space between the lines indicates a slow change in height. A little space indicates a very large or quick change in height. So when the lines are spread out, we have a, like you see here, okay, when they're spread out here, it's a gentle slope. When you see the lines really close together like here or up here, that's a very steep slope. These topography lines are called equipotential lines when we use them to represent the electric potential. They all have the same potential value, as you can see from the side view. Okay? They represent the lines where the electric potential is the same. The closer the lines are, the faster the charge or the change in voltage. The bigger the change in voltage, the larger the electric field. It turns out that when you find these potential lines, the electric field lines are drawn perpendicular to these electric field lines. The direction of the electric field lines are always perpendicular to the equipotential lines. The electric field lines are farther apart when the equipotential lines are farther apart. The electric field goes from high to low potential, just like a positive charge. Okay, so here we see the equipotential lines are given in green. The electric field lines are given in blue. Notice that the blue lines are perpendicular to the green lines. For a positive charge like this one, the equipotential lines are positive and decrease to 0 at infinity. A negative charge would be surrounded by negative equipotential lines, which would also go to 0 at infinity. More interesting, equipotential lines, like the topography lines on the map, are generated by more complex charge configurations. So here are equipotential lines. In this configuration, it was created by a positive charge to the left of the 20-volt line and a negative charge on the right of a negative 20-volt line. So this configuration that we see here was created by a positive and a negative charge. Notice that the red arrows indicate the direction of the electric field, which lines are drawn perpendicular. Now, the way that you would continue this is, see how this hits this line here? Well, it would have to be perpendicular, and then perpendicular, and then perpendicular to here, and then perpendicular here. Notice here, it would curve, go straight, and curve. Here, it would curve, go straight, and then curve up. So you can see that you would form this equipotential surface here, which is the blue lines. The red lines indicate the electric field lines. At point A in the diagram, what is the direction of the electric field? Is it going to be up, down, left, or right? Pause the video if you need to and select your answer. Okay, so let's check and see if you have the right answer. The answer should be D, goes to the right. How much work is done by an external force on a plus 10 microcoulomb charge that moves from point C to B? Go ahead and pause the video and solve this problem. Okay, so let's go ahead and take a look at our answer. Work is equal to Q delta V. We're going from 150 to 0, so 150 minus 0 gives us 150. 150 times 10 times 10 to the minus 6 is going to give us 1.5 times 10 to the minus 3 joules. How much work is done by an external force on a minus 10 microcoulomb charge that moves from point C to B? Go ahead and pause the video now and solve the problem. Okay, so let's take a look. Work is equal to Q delta V. We end up with negative 10 times 10 to the minus 6 coulombs times 150 minus 0, and that gives us negative 1.5 times 10 to the minus 3 joules. Okay, and this is the end of this video. We'll go ahead and start the next video, the next information in the next video.